So first question, what does this program, print new B, actually print out on the screen? Please vote on the poll. Okay, so the correct answer is AB. Given that quite a few people have said BB and some other things, I'm going to try and explain why. So first of all, this method print takes an object of type A, and we've passed it of something of type B. What is the name of the principle that that is abiding by, that we're allowed to do that because of? Yeah, the substitution principle says that since B is a subtype of A, anywhere I want an A, I can pass the B instead. By the substitution principle, this code compiles. Hooray. So we then we pass this B into our print method, and the first thing it does is says print value.get. So get is the name of the field in the object, and fields do not have any sort of dynamic polymorphic behavior. Right, so the field is resolved statically based on the type of the object. So since the object's type is A, the field that we get is the version of get from class A, not the version of get from class B, even though the thing is really a B. Okay, so I'm just recapping what we did last lecture. Value.get is determined by the static type of A, so we get the first one. We get the string A for that. The second line calls the method get, and get is overridden in the subclass B. Remember the difference between overriding and overloading. So because get is overridden in B, we get dynamic polymorphic behavior. It's a virtual method call, dynamic dispatch. These are all words you should remember from last time. And the value returned is B, and so it prints B. So we get AB. If you said AB, good job. If you said BB, that was probably because you were thinking about the fields being dealt with dynamically as well as the methods. That's not right. Fields are statically based on type. If you said AA and BA, I'm not quite sure why you said that. Come talk to me at the end, or talk to your supervisor if you're confused about what this does. So here are some other things that happened in the drop-in session yesterday. We found an error in the test for product of other elements, and we've now fixed that error. So if you've been having sort of like mysterious failures when you're trying to do that test, just push another commit, and hopefully that will now pass. This one was really fun. If you have non-ASCII characters in your path name, then coverage testing in IntelliJ seems to not work, and you get like a page of exceptions that says illegal argument exception, index out of bounds, blah. That's just like awful. You can use Maven instead if you need to do that. So let me just show you how that works. So here is my IntelliJ with my Fibonacci thing in it. And because it's a Maven project, IntelliJ has given me this extra tab right up in the top right-hand corner that says Maven. If I click that, I can do all sorts of stuff. So when you click it the first time, it will look a bit like this. So to run the tests, the test coverage thing using Maven, you do two things. First of all, you go to cycle, you run test. So this is using Maven to run the tests rather than IntelliJ. They run, and you can see here that they haven't failed or had any errors. Then you open plugins, Jacoco, report. So this is the Maven plugin that computes test coverage, and it's now analyzing the results of running the test and making a website that contains all of my test results, which you can find inside the target directory site, Jacoco. This one. Where's it open? in browser, there we are. So then open in browser, hello. Yeah. And you get basically roughly the same sort of thing you get in IntelliJ, but just in your web browser instead. So it tells you which lines had which coverage and where they were, and you can do it that way. Sorry about that. JetBrains is actually a Russian company, so I would expect that they would have seen Unicode characters quite a lot, but it just doesn't work. The final thing is if you're having Git problems and you're it works on the command line, but it doesn't work in IntelliJ, then make sure that IntelliJ has got the right path. So in Preferences, which is here on a Mac, if you search for Git, you'll find that there's a page here where it says path to Git executable. If that's wrong, or pointing to the wrong one on your machine, then it won't work properly. You'll get different behavior on the command line than the other one. So check that if you're having any problems. And then one final thing that came up is something that I've just forgotten to teach you. So this is the this syntax. So let me just explain to you what this means. So this one at the bottom here is a constructor. And the syntax of a constructor, remember, is that you just write the name of the class and then the arguments that you want the constructor to take. So this is taking an int I, and it's setting the field I in the current object to be the value I. Now, I've also provided another constructor, and it's an overloaded constructor, right? The parameters are different, but the name of the method is the same. And this constructor takes no arguments. And what it does is it has this weird this bracket syntax, and that just says, invoke the other constructor, passing the number 4 to it. So the example with the no arguments constructor just says, delegate to the other constructor, passing the value 4 in there. This is a really common thing, because often you have to you have a default way of constructing your object, and then you have a more advanced way with lots of different options. And so this lets you sort of share the code between your constructors and not have to write it more than one time. The syntax looks weird, but it's just think of it as sort of calling the method constructor calling the constructor method with the argument 4. So that's what that means. You'll see it in some of the exercises on Chime that's the way the code has been written. Right. Today, life cycle of an object. So by the end of the lecture, I want you to know the process that Java uses for initializing an object. And the reason why this is important is that there are tricky sort of swamp-infested areas around object creation where you just want to try and avoid when you're writing code so that you don't get weird bugs in your program. And we're going to talk about something called a destructor and a finalizer, and I want you to know the difference between those things. And then these two crazy initials are resource acquisition is initialization. That's will be familiar to those of you who've done some C++. TWR is try with resources, which is a Java thing, and I'm going to show you what they are and what the difference is. And then a very, very high-level idea about what a garbage collector is. I'm not expecting you to be able to implement one. I just want you to know what it is and roughly how it might work. OK, so let's have a look at some object construction. So I'm going to write some like a experiment where I'm going to get the Java language to print out messages to me when it does stuff, so that I can then look at the order that things happen when it creates objects. So what I'm going to do first is I'm going to say, imagine my object had a final constant field, say called constant, and I'm going to initialize it to be a string. The string is returned by this static method, so it lets me get a side effect in there which says, create this constant. It's going to have the value null. It's really exciting. But as a side effect, please print this thing out, print this message out, so that when I run my code, it's going to print stuff all over the place, and I'm going to see the order in which things happen. So first of all, let's just see what happens. I'm just going to refer to the object, refer to the class, but I'm not going to do anything else. So when I run this program, see if you can think about what's going to happen. The answer is nothing, right? It doesn't print anything at all. The compiler, the language hasn't tried to do anything yet with the type. It just knows it exists, but it hasn't tried to do anything on it. If I now try and call the static method on this type, print, then Java has to actually load that class into memory and get ready to use it so it can use that static initializer. And so what you'll see, that static method, is it has to initialize all the static fields. So here it says, this is the hello world that I wanted it to print, but before it printed that, it printed out this constant message. So when it loaded the class, the first thing that it had to do was initialize this static field constant. So just because I used something in the class, I used this print method, it then had to load the whole class, and when it loaded the whole class, it had to print out this message constant because it initialized that field. You can do other forms of initialization. This is a static initializer block. So you can just write that in your program, that's fine. It just says, run this code when you load the class. So what happens here? Well, I can run it again, and now it prints constant, and then it prints static initializer. The static initializers are run in the order they appear in the file. String constant 2. So these are going to be run in the order that they're printed in the file. So it's going to print constant, then it's going to print static initializer, and then it's going to print constant 2. So it doesn't matter, they're different kinds of things, they just get run in the order they appear in the file. Okay, so that's good. Now, if instead of printing something here, I just create a new one of these objects, what am I expecting it to print now? What does it have to do before it can create a new one of something? It has to load the class. So therefore, we would expect it to print almost the same thing as it printed last time, but without the hello world, because I haven't called print hello world anymore. So in order to create an instance of the class, in order to create the object, I have to also load the class beforehand, and so it just prints exactly the same thing that it printed before. All of the static initializers get loaded. Okay, so now let's see what happens if we add some fields. So I'm going to add a field, in here. Private final string. Okay, so this is an instance field, right? It's not static, so I get one of these for every single instance of the object I create. So if I now print out the order of what happens here, then you can see that what it does is it runs all the static stuff first, and then it runs the instance stuff. So the static stuff gets done in the order that it appears in the file, but even though this instance field is in the middle of all the static things, it doesn't get run until later. Right? So it completely loads the class, then it can then create the object. So that kind of makes sense that they have to be like that. Instance fields are also loaded in the order that they appear textually in the file. So I could have another one of these down here. And this will print instance and then instance 2, one after the other. Okay, so now I'm going to create another one of these objects, and I'm going to ask you what it is that this will print now. So I'm going to create 2 constructed objects. So what's this going to do? Maybe you don't have to tell me exactly what it's going to print, but what's the general idea about what it's going to do? Yep. Yeah, so it's going to do everything that it did for the first object. So it's going to print all of this. And then for the second object, it's only going to print the instance stuff again, because it's already done all the static things for loading the class. It's already there. So the static initializer stuff sort of happens when it needs to in the background. Like the first time you use that class, then it happens. And it just happens for you, like in the background, and then it won't happen again, because it's already been loaded at that point. So you can see here, I've got my static stuff at the beginning, and then I've got two goes at doing the instance variables. All right, so now I'm going to add a constructor. So when we think about what this is going to print, there are there are two hypotheses, right? One is that it's the same as static, and it does things in the order they appear in the source file. The other one is that it does the fields first and then the constructor second. And it's that one. So you get all the static stuff in the order it appears in the file. You get all the instance fields in the order they appear in the file. Then you get the constructor. So instance fields constructor, instance fields constructor. OK, so you're all like, Andy, why does this matter? Right, why should I care about this? Well, if you're defining your class and you've initialized some parts of your class with fields and some part of your class with a constructor, and then you're referring to those things from each other. So you've set up a field and then you've copied a value, then you've used that value from a field in your constructor, for example. You need to know whether it's going to be initialized by the time that you want to use it or not. So sometimes you'll get warned about it. So here's an example where if I try and initialize constant to be constant 2, I get red squiggles. And Java says you can't do this, it's an illegal forward reference. Because it knows that constant 2 won't be initialized by the time in which you try to initialize constant 1. So in some cases, it will warn you. In some cases, you can write programs where it just can't tell. I'm going to show you one of those in a minute. So this is why we care about initialization order, because if you just completely initialize your class in the constructors, then you don't care about when the fields get initialized, right? But if you have a mix of these things, or if you have a mix of static things and instance things, then you need to worry about what's going to happen. One really common pattern is to use cached data, right? So you've got some big complicated thing. So when the class is loaded, you use some static method to initialize a big array or something like that, and then you use it from the objects. So you need to make sure you've got all of your static stuff done before the instance stuff happens, so you want to understand the order of these things. OK, so that's all just some arbitrary rules, and that's all fine. But it gets a little bit more interesting when you also add in inheritance. So I'm going to add another class here called superObject. And in order we can tell the difference, I'm just going to change the print method. So, and I'm going to change my constructed object to extend my superObject. And I'm only going to do this once, because otherwise the screen gets full. All right, so I've only made one instance of constructed object here. What's it done? Well, the first thing it's tried to do is it said I need to load the class for constructed object. And in order to load the class for constructed object, I need to load the class for its superclass, superObject. And so the first three things it's done are the static initializers for superObject, and then the static initializers for constructed object. So that's the class loading bit. That's the first one. And then you've said, I need to create a new instance of this constructed object class. But constructed object extends from superObject. It's everything that superObject is. So first of all, I have to make an instance of the parent class. So here, I'm going to make an instance of the parent class. So I call all the fields on the parent class to initialize them. Then I call the constructor on the parent class to construct it. And then I construct the subclass constructed object instance and constructed instance 2, and then constructed object constructor. Right, so this is called chaining. What's happened is, to create an instance of constructed object, I needed an instance of superObject, so I had to go and do that first. And all of the things I had to do that had to be done before then, and so on up and down the stack. OK, now I can make this even worse, because what if my constructor takes an argument? Okay. So now the only way to make an instance of superObject is to pass a string to the constructor. And so constructed object it no longer compiles, because it says, I don't know how to make instances of superObject for you anymore, because it needs to take a string, and I don't know what string to use. So this error message here says there's no default constructor available. Right? There's no thing with no arguments, so I don't know what to do. And so what you have to do is you have to tell it by using this super call. So you remember we have this with brackets to refer to constructors in my class. Super with brackets refers to constructors in the superclass. And I can say here, here is your argument. OK, so in this constructor, it's now gone, I've now said, well, when you're constructing constructed objects, I know that you need an instance of the superclass, and now I'm telling you how to create it by passing it this string. So this is all fine. It'll print the same stuff, right? So first of all, it creates the class, needs the superclass first, initializes all of the static things, then it creates the super object, initializes the fields in the constructor, and then all the way down. So here's the gotcha, which is in here. What if rather than passing a string, I print? So we initialize the class. We initialize the superclass. We initialize the class, and then here we print out hello. So we've started invoking the constructor here. Then we call super object stuff, and then we carry on doing the constructor there. Right. So what Java does is it says, when you're writing executing this code, do the super bit first, let all of that run, and then come back and then do the rest of the class initialization. So it runs the first line of your constructor, the super bit, then it loads the superclass and initializes at that point, and then it comes back again. So print hello gets called because I need an argument for the super constructor. So it prints out hello. Then it goes, hold everything. I need to create an instance of this superclass now at this point. And so these two fields get initialized. Right? There's no code saying initialize these fields. It just happens. Then it calls the constructor on the superclass, and then it finishes off doing the object. OK, so this is like you're going down the roads of disaster here. If you write code and you use your own class in a method call, which you then pass to the super constructor, you're starting to get into this mess about what's happening in what order, and it gets a little bit subtle. So for example, let me show you color point. So I have a class point. It takes an x and a y, and when you construct it, it goes, I'm going to invent a string to use for the name. So I'm going to build the name, and the name is going to be x plus y in square brackets, or x comma y in square brackets, and then I've got toString, which returns the name. So that's good. So now I have a color point, and what color point does is it has a color as well. So here the syntax is super brackets, and I have to pass both an x and a y, two integers, because that's what the constructor of the superclass wants. And I've also got this color, and then makeName is going to use whatever the name of the superclass is, and it's going to add color on the end. Right, that all seems sensible. If I run this code, you'll see that it doesn't work at all. And rather than printing the color, it prints null. Right? Because what's happened is we try to create a new color point. So it starts executing the constructor. The first thing the constructor does is it says execute the superclass's constructor. We go to the superclass, and we initialize the fields and run the constructor, and we run makeName. So makeName is a method. It's overloaded. It's overridden, so it's implemented in the subclass. So we don't call this version of makeName. We call this version of makeName. This version of makeName refers to this field color, which we haven't initialized yet. So even though this thing is final and can never change, we've read two values from it. We've read null from it, and then later on in the rest of the program, we'll read the actual value of color from it. So this is why I'm showing you this stuff, because you can see how you can disappear down a rabbit hole with this stuff here. The general rule is to avoid this. Right? Because what's happened here is inside the constructor, I've referred to wider state of the class which I'm currently initializing. And because I've done that, I've left myself open for someone to change that behavior, add some new things on which aren't initialized there, and you get into a mess. In the Effective Java book, you'll see that there's one of the recommendations is to do no work in a constructor. And what that means is just initialize the fields, don't try and calculate anything, and it's trying to avoid these, among other things, these kind of situations where you can get into a loop of trying to do something with an object that isn't initialized yet. OK, so static initialization happens first. It's done in textual order. It only happens once when you load the class. That happens for you in the background the first time you refer to it. Then you allocate the memory for the object, initialize the object, and run the constructor. And when you are constructing objects of like inherited types, then you have to chain the constructors up. To construct an instance of the subclass, I have to construct an instance of the superclass all the way up recursively up the inheritance chain. If you don't have a default no-args constructor, then you have to tell Java explicitly which one you want to call. Sometimes you will see, oops, wrong editor. Sometimes you will see like, where's my object gone? People will write just that in their constructors, like super with no arguments. That just means call the default constructor. So it's like an explicit way of saying do the thing that you would do anyway by default. So you'll sometimes see that in code. If your classes have explicit constructors with arguments, you need to super them to say what they are. Here we have super Bob. Okay, so that concludes object initialization. How do we get one? Now we need to think about how do we get rid of one. So objects are created, used, and then eventually destroyed. The destruction of objects is really language specific, like when they disappear and how. And intuitively, deterministic destruction is a really nice thing. Like knowing when an object is going to disappear is really useful. So in C++, I can say new my class, that allocates a my class on the heap and returns a pointer to it. And then because C++ doesn't do this garbage collection thing, I have to explicitly delete it myself, so I know that my class will be destroyed when I call delete. Or on C++, you can create a new object on the stack. So this syntax here, although it doesn't look like it, actually allocates a new instance of my class on the stack. And remember that from lecture 4, when we have stacks, they unroll automatically when we return from the function. So as we return from useSmartPointer, this thing will be deleted guaranteed. So C++ makes strict guarantees about when things will be deleted or otherwise. One of the reasons why it's useful to know when things are being deleted is that you might want to clean up some mess when you're deleting your object. So here in an example, I open a file. And what I would like to do is say that when I delete the object, I'd also like to close the file, because otherwise I run out of the maximum number of open files my operating system will let me have and my program crashes. So C++ code again. Here is a destructor. You write exactly the same thing as you do for a constructor, but you precede it by a tilde character. And this destructor says when you delete this file reader object, you should close the resource that you acquired. This is called resource acquisition is initialization. And what it means is you acquire your resources when you construct your object, and you free your resources when you delete your object. And because you know when the objects are going to be deleted, you can then build code that means that you never accidentally forget to close a file. So in this example on the right-hand side, file reader is allocated on the stack. So the file reader object goes on the stack frame. When the main method returns, the stack frame is unwound, the destructor is called, and the file is freed. Can't do that in Java. The reason why you can't do that in Java is that Java doesn't require you to explicitly delete your objects. In fact, it doesn't let you. And instead what it does is it says that someone else is going to take care of that. It's called the garbage collector. And again, this is a design decision made by the people who designed the language, and they said one of the many reasons why C++ programs crash is they forget to free the objects that they've created on the heap, and so therefore we're not going to let people do that, we're going to do it for them. Python is garbage collected, OCaml is garbage collected, JavaScript is garbage collected, C++ is optionally garbage collected. You can use a library to do this thing, but in Java you always get it. So what's going to happen is that we're going to just create objects and throw them on the heap. And the system is somehow, magically in the background, going to work out for us when we're finished with that object, and it's going to free it when it does so. So the immediate ramification of that is that it might not be freed at the point that your method returns, because the garbage collector makes no guarantees about noticing immediately. So what they did in the original version of Java was they provided a thing called a finalizer. So there's a method in the in object called finalize, and it's the method that gets run when the garbage collector frees your object. And it's got this horizontal line through it in IntelliJ because it's deprecated. Like, they really wish they hadn't done this. But we're going to use it anyway. Oops, wrong kind of. So if I say new finalizer, so I'm going to just create a new one of these in my main method and run my program, then what you'll notice is it doesn't print anything at all. Right? So one of the options for the garbage collector is to go, hey, the program's finished. I don't need to collect any objects. I'll just throw the whole thing away. Right? So the first thing about finalizers is they may not ever be run. So it's like a finalizer if I choose to run it, rather than a guaranteed finalizer. The other thing is that they only get run when the garbage collector does something. So if you do something crazy, like this, then you'll start to, I'm just going to not use the debugger because it gets a bit slow. Then you start to see it do stuff. Because what's happened is you've been throwing finalizers onto the heap, and at some point the garbage collector's gone, hey, there's no more room. I'm going to have to free up some of the junk here. So it's run and it's collected a load of the objects that you've just left lying around, and it's run the finalizers on that point. So it's printed out I'm free. But I created, I don't know, is that 1 million or 10 million? A lot of finalizers. It hasn't printed that many I'm frees. It's just done the minimum number it needed to do while it was collecting the code. So Java provides finalizers. They get run when the garbage collector collects your object. But they might not get run ever, because the garbage collector might not run before your program exits. And they might not get run when you want them to, because the garbage collector chooses when it wants to run, not you. So do not try and do destructor-style C++ stuff in finalizers in Java, because it just won't work. You'll just get weird bugs. So we can't have a conventional destructor in the C++ sense in Java, because there's no hook to get that destructor to be run, because the garbage collector is going to run when it wants to run instead. And so these finalizers are really not going to help us. Java added a programming construct called try with resources to try and give you an alternative to RAII, try to give you an alternative as a way of trying to release your resources sensibly. So too many IntelliJs today. What does that look like? Well, so imagine my this try with resources object, right? It's going to have a constructor, and it's going to acquire expensive stuff. Okay, so that might be opening files. It might be like making connections to databases. It might be like taking a lock on the GPU so I can train a neural network, something like that, though. So it's like it's grabbed onto some finite resource that the system has, and I'd like to release that after it's been used. And so the way you do that is you say try. So you construct the object in brackets at the beginning of a try block. So you write try, and then in brackets you construct the object you want, and then inside this block, object exists, and outside this block, object still exists, but close will have been called. So this squiggly line here says, well, you've given me a thing that you want me to close automatically, but you haven't told me how to do it. You need to implement a interface. Hello, just fix my code. All right, no, all right, fine. So there's an interface called closable, and closable defines a single method, which is the method that the try with resources block will call at the point at which it needs to close your object. So you have to implement closable, and then when you've implemented closable, you can say, release expensive stuff, and then this thing will now moan at me. I'm doing exceptions next time. We'll now close the object. So I can print out what goes on, just like I did before. Acquire and release and start and execute. So we start our code, we create a new instance of try with resources, so it runs the constructor and it acquires expensive connection to database or GPU locks or whatever. We execute the code, and then as we leave this block here, the close method gets called, and so the program prints out release. And then after that point, the object still exists because the finalizer hasn't run, probably, can't guarantee it, but we can then carry on with the rest of our program. So you have to be careful with resources in your program, because once you acquire them, they're gone, right? So if you don't manage acquiring and releasing resources properly, then you run out of them at some point and your program crashes. Normally it crashes in production because in your tests you haven't done it enough to actually cause it to run out of resources. So it's like an embarrassing way that it breaks. And try with resources is a nice structure to make it like guaranteed that close will get called at the end of your block. You've all seen exceptions already because you've seen the demo code on Chime where it's like it just throws an error, like unsupported operation, if it doesn't like what you're doing. This code here that I write in this block could throw an exception and just like exit halfway through the block. It could go, unsupported operation, you haven't implemented your exercise yet. It could try and exit. Try with resources will still call closed, right? So it guarantees that it will call closed regardless of how you exit that block. If you return from the function, close get called. If you throw an exception, close get called. If you leave the end of the block, close gets called. So it gives you like a guarantee about the safety of your program. And it's as close as Java can get to the C++ version, where it just sort of like you write a destructor and things gets tidied up for you. So how exactly does garbage collection work? Well, let me rephrase that. How approximately does garbage collection work? So what happens is you run your Java program, and another process runs in the background, which is constantly like monitoring your program and looking for things to delete. Now, running this process is obviously not free, right? It takes up resources to run the garbage collector. So if your program creates lots of objects, then the garbage collector has to run. You might notice it. And so it can give like noticeable pauses to your program. So one kind of garbage collector is a stop the world garbage collector. And what that means is it stops your whole program executing, like pauses it, goes around, tidies up the mess, and then resumes your program again. So stop the world garbage collectors take a lock, they stop your program, they clean up the mess, and then they resume you again. You notice that in interactive programs, right? Because you're trying to do something, you're clicking on the UI, and the garbage collector's decided to run, so the program becomes unresponsive for half a second while it cleans up, and then it carries on again. Garbage collection minimizes memory leaks, but it doesn't prevent them. So you can still leak things by making them uncollectible to the garbage collector. So let me show you how you can do that. This is like a really obvious example, but you could get much more creative. I'm going to leak some objects. So garbage collector can't do anything here, right? Because I've added more and more of these objects to my list L, but I could still do things with this list L here, right? It's still in scope. So the garbage collector doesn't know whether I'm going to use it again in future, and so it can't collect them. So if this, say I was doing this, right? The lifetime of that static L is the lifetime of my entire program. So I've created this thing, I've used up a load of memory, and then I've just sort of stashed it in L, and because it's reachable through some convoluted route, the garbage collector can't free it up, and so it just sits there using up resources. That's the closest you can get to like a memory leak in Java. You have to like leak quite a lot to cause it a problem. Do-do-do-do-do. So if this is successful, then Java will run out of memory. What it's busily doing at the moment is trying to use up all the resources on my laptop to try and run this program. Maybe this wasn't a good idea. If it doesn't crash, like the whole machine, what you'll get here is a stack trace that says I ran out of heap space. It will say I tried to allocate an object, and I really couldn't do it. This is getting warm. I'm just going to try and carry on teaching while that runs. See what happens. So stop the world means pause the program, collect the garbage, and then resume. You need to know about that because if your JVM is running with that kind of garbage collector and you're building an interactive app, then you're going to suffer like interactive jitters when you collect objects. And you like say, well, Andy, I don't get to choose when the garbage collector runs. And that's true, you don't. But you do get to choose when you allocate objects. So one way that people try and write programs which work well in interactive mode with the stop the world garbage collector is they don't allocate objects while they're doing the interactive bit. You allocate them beforehand, you cache them, or you do something like that, and then you don't cause any new heap activity, so the garbage collector won't run while you're doing the interactive stuff. Another kind of garbage collector is an incremental garbage collector. Actually, you can have incremental stop-the-world garbage collectors if you want. Incremental means just like you collect in multiple phases. So you do like a bit of the work, and then you go, now you can run a bit more. Then you do a bit more of the work, and then you can run a bit more. Sorry, the fan is going now. Hey, there we are. And so you try and do like more frequent, smaller pauses than less frequent, big, long pauses, so by doing something incremental. And there's also such a thing as a concurrent garbage collector, which just runs without stopping your program. These are really hard to write, and there aren't many of them. Java has stop the world collections. Well, it has a... Java is changing its garbage collector at the moment for one which has phases, and some of those phases are stop the world, and some of them are not. That's enough that you need to know. Here's one potential algorithm for doing garbage collection. There are many. This one has performance problems, but it gives you an idea about the kind of thing you do. It's called mark and sweep. So what you do is you start off and you say, these are all the references that I'm currently using. So they're like the static fields in all my classes, the variables which are in scope in this particular function, the things which are on the stack. And you start with those references, and you follow all those references recursively, marking every object you get to. So you're like, I've got an object, it has a field, I'm going to look in the field, and you just walk around the heap, like ticking each one, saying, I reached you. That's the mark phase. When you finish walking the heap and ticking things, you then do a sweep, which is you walk over the entire heap looking for things that haven't been ticked, and then you delete them. So in this case, we had X, Y, and Z. We followed the edges, we found objects, we followed more edges, we found objects linked from those objects, but we never got to this little pair over here, which reference each other, but no one else. And so because they're unreachable in my program, the garbage collector concludes that you don't need them and it can free them. So mark, go around ticking boxes saying we're gonna free these objects, and then sweep, you then clean up the mess. This causes long pauses because you stop the whole program while you walk around the heap, like you walk over all of your memory, so it's not used practically, but I just want you to have a rough idea about how one might work, like how the idea could be done. Okay, so that's all for today. Next lecture, we're going to do collections and object comparison.